Dear students, this is Naresh Reddy. Welcome to this session on communication systems. In this session, I will try to give some important questions for this subject, communication systems. If you see the first question, this is about amplitude modulation. Here an AM signal is given where this message signal MT is uniformly distributed in the interval -2, 2. Then we have to find the ratio of PC to PSB, the carrier power to sideband power we have to find out. So what is the specialty of this question is, here this message signal is a random signal, okay. So the density function of this random signal is given. So if you plot the density function of this random message signal, so density function of MT. So message signal is uniformly distributed in the interval -2, 2. So uniformly distributed means the density function is constant like this. Okay. Then what is the height will be 1/4. Okay. The total area under density function should be equals to 1. So the height should be equals to 1/4. So here the density function of message signal is given. And if you see the expression of AM signal, it is in the standard form. Okay. So what is the standard expression for the AM signal is AC into 1 plus KAMT cos 2 pi FCT. This is okay. So it is a standard AM expression where Ka is the amplitude sensitivity of AM modulator. So if you expand it, this is AC cos 2 pi FCT plus AC KAMT cos 2 pi FCT. Okay. So if you try to get the total power here, PT, that will be AC squared by 2. AC cos, the power is AC squared by 2. Okay. Then what is the power of this is? It is in the form of Vm cos. The power will be Vm squared by 2. So that is AC squared Ka squared M squared T by 2. Okay. So here this is, we write as M squared T bar. Okay. And this M squared T bar here specifies power of the message signal. I'm denoting with PM. Okay. So here the total AM power, if you take AC squared by 2 common, that will be 1 plus Ka square PM. So it is a standard formula to find AM power. Okay. Now here we have to find out the carrier power to sideband power ratio. We have to find out. So here PT you can write as AC squared by 2 plus AC square Ka square PM by 2. Okay. So this is the total AM power PC plus PS you can write as. So from comparison, PC equals to AC squared by 2, the power of this carrier term. Okay. And here this is the modulated term. The power of this modulated term is also called as sideband power. And that sideband power will be AC square Ka square PM by 2. So here, yes, we have to find out PC by PSB, we have to find out. Okay. And PC equals to AC squared by 2. And PSB equals to AC square Ka square PM by 2. And AC square by 2, AC square by 2 will be cancelled. This is 1 by Ka square PM. So this is the formula to find out PC by PSB, where PM is the power of the message signal. So let's find out the power of the message signal first. Okay. So here the power of the message signal I'm denoting with PM equals to, where message signal is a random signal here. How to find the power of a random signal is the mean square value will give its power. So that is expectation of M square T. The mean square value of MT will give you the power of the corresponding random signal MT. The mean square value is nothing but expectation of M square T is nothing but mean square value of MT. That will give you power of message signal. So this is integration M square into density function of that message signal Fm of M, where message signal takes the values from -2 to 2. This is. So here it is -2 to 2 M square And what is fm of m? What is the value of this? 1 by 4. And if you substitute here 1 by 4 dm and do the integration and substitute the limits, then you come to know this will be 4 by 3. This is the power of the message signal. Now what about Ka here? So if you compare this AM expression, the given AM expression with standard AM expression, that is AC into 1 plus Ka mt cos omega ct, then Ka will be equals to 0.5. Okay, then what will be this PC by PSB? So that will be equals to 1 by Ka is how much? 0.5 square. And what is the power of the message signal? That is 4 by 3. So this will be equals to 3 by 1. This is, so 0.25 into 4, that will be 1. So 3 by 1, that will be 3. Okay, so the answer here will be 3 here. So which option will be correct here is option C will be correct. Okay, so here the random signals concept was involved in solving the question here based on amplitude modulation. Okay, if you see the next question here, so most of the students are getting confusion, okay, in finding complex envelope of a signal and pre-envelope of a signal. So I want to do a problem on complex envelope here, finding the complex envelope. So it is a previously given gate question only. Okay, so we have to find complex envelope of this baseband signal xt, okay, which is centered about f is equals to 1 by 2 hertz. Okay, so what is the center frequency here? Okay, so it is a sinusoidal signal, okay, having the frequency half hertz, 1 by 2 hertz. So for this bandpass signal, we have to find complex envelope, and here some options are given here. So let me give you some formulas here first. Okay, so if you take a bandpass signal xt, okay, so for that bandpass signal xt, complex envelope of xt, okay, where xt is a bandpass signal. Okay, and to find the complex envelope of a bandpass signal, first you have to write that signal xt in this form. Okay, how to write that signal xt is the combination of cos and sine terms you have to write. So that is xit cos 2 pi fct, okay, plus xqt sine 2 pi fct. Yes, students, to find the complex envelope of the given signal, first you have to write that signal in this form. You have to write as a combination of cos and sine. Okay, this coefficient along the cosine term, this is called as in phase component xit, in phase component of xt, and the coefficient along this sine signal xqt, what you say, this is called as quadrature component of xt. So it is in phase component and this is quadrature component. So once you manage to write xt in this form, okay, then the complex envelope, I'm denoting with xcet, will be equals to, this is xit minus jxqt. This is a formula. Okay, and if your signal, the bandpass signal xt in this form, okay, xit cos minus xqt sine, then complex envelope will be xit plus jxqt. Okay, so if it is plus here, then you will get minus here in finding complex envelope, and if it is minus here in finding complex envelope, you will get plus here. Okay, now if you come to the, okay, the given signal here xt, okay, so if you, we have to write this as a combination of cos and sine. For this, just try to expand it. Okay, sine a minus b, sine a cos b minus cos a sine b. So if you expand, then what you will get is, I'm writing here itself. So this is minus root 2. Okay, and here sine pi x by pi x, you can write as sinc x, you can write. So I'm writing this as sinc function, sinc t by 5. This is, okay, and sine a minus b, sine a cos b minus cos a sine b. Okay, sine a cos b cos pi by 4. Okay, sine a cos b minus cos a sine b. So minus minus becomes what? Plus here. So plus root 2 sinc t by phi, okay, cos A sin B, cos pi t sin pi by 4. Okay, now I'm writing this signal xt as, we have to write in the form of xiT cos, okay, and xqt sin, cos 2 pi fct sin 2 pi fct. Okay, where the center frequency here, the fc is what here, what is the center frequency fc given? Half hertz. Okay, so this is here, you can say, yes, this is cos 2 pi fct term and this is sin 2 pi fct term where fc is half hertz. Now, yes, so we can write this as root 2 sinc t by phi and sin pi by 4 cos pi t. Okay, first I'm writing this as the first term and this is the second term. I'm writing cosine as the first term and sine as the second term. So it is minus root 2, this is sinc t by phi cos pi by 4 sin pi t. Okay, now you can see it is in the form of, okay, xit, this is xit cos 2 pi fct minus, it is minus, and it is xqt sin 2 pi fct. Okay, then what will be the complex envelope will be? Okay, yes, the complex envelope xce of t will be equals to, so I can write xit plus jxqt will be xit plus jxqt. So xit is what? Root 2 sinc t by phi sin pi by 4 xit plus jxqt. xqt is root 2 sinc t by phi, this is cos pi by 4. Okay, now if you take root 2 sinc t by phi common, okay, if you see the options are in this form, in the form of exponential function. So to write in the form of exponential functions, I'm taking this root 2 sinc t by phi common. So this will be sin pi by 4 plus j cos pi by 4. Okay, now cos x plus I sin x, you can write e power jx, you can write in the form of exponential function, you can write. So to write in the form of exponential function, okay, to write in the form of exponential function, the given, okay, should be in the form of cos x plus I sin x. Okay, so for that I will take this, okay, I common here, this is j, I'm taking common, j root 2 sinc t by phi. Okay, now if you take j common here, this is cos pi by 4. Okay, it is 1 by j means minus j, so minus j sin pi by 4 this is. Okay, now it will be, j means you can write e power j pi by 2, you can write e power j pi by 2, cos pi by 2 plus I sin pi by 2 will be I only, that will be j, I mean to say. So j you can write e power j pi by 2, so root 2 sinc t by phi, this is cos x minus I sin x, you can write e power minus jx, you can write e power minus j pi by 4. Okay, now it will be, because if you see all the options, there is no j term. Okay, there is no j term, that's what I'm writing this j as e power j pi by 2 I'm writing. Okay, now it will be equals to, so this is root 2, yes, sinc t by phi, I can write as sinc x is sin pi x by pi x, so this is sin pi t by phi by, okay, pi t by phi, sin pi x by pi x is sinc x. Okay, now Yes, this is e power j pi by 2 into e power minus j pi by 4. It is 90 minus 45. Okay, 90 minus 45 will be 45 only. So it is e power j 45 means pi by 4. So this is the complex envelope of the given bandpass signal. So root 2 Singh t by 5 e power j pi by 4. So which option will be correct here is, okay, so option C will be correct here. Okay, now let me give you some formulas here. What that formulas here is, I want to give you the formula about pre-envelope of a bandpass signal. Okay, it is given by xt plus jx cap t. This is, so this is the formula to find out pre-envelope of a bandpass signal xt, and this is xt plus jx cap t, where x cap t is Hilbert transformation of xt. This is, okay, so finding pre-envelope never given in gate examination, till now never given, but maybe you can expect, so take care of this. And what is the relation between pre-envelope and complex envelope of a signal is, so xp of t equals to xce of t into e power j 2 pi fct. Okay, so it is a relation between complex envelope and pre-envelope of a signal. Okay, and one more thing here is, I can write xt. If pre-envelope of a signal is given, then how to find the corresponding bandpass signal? So the bandpass signal xt simply equals to the real part of this pre-envelope. Okay, so this is, yeah, x cap t is the Hilbert transformation of xt. That's okay, fine. Now the given bandpass signal xt will be equals to, this is real part of pre-envelope of that signal. Okay, or you can write like this also, this is real part of pre-envelope, you can write as complex envelope of the signal. This is xce of t into e power j 2 pi fct. Okay, so this is, so these are some formulas about the relation between complex envelope and pre-envelope of a signal, and how to find the given bandpass signal xt from its pre-envelope and from its complex envelope. Okay, so take care of these formulas. Okay, if you see the next question here, this is about angle modulation, and most of the students are actually, generally they will ask me doubts about finding, they're getting actually confusion in finding fi max, maximum instantaneous frequency, minimum instantaneous frequency, how to find the frequency deviation, total frequency swing. So they're getting actually the confusion in getting these parameters. So I will try to I mean to say overcome this confusion for you. Okay, from this question. Okay, so all these parameters I'm going to find out here. Okay, I think your doubts will be clarified in finding these parameters from this question. Yes, here this message signal mt, what you say, it is getting phase modulated, where the PM signal generated is cos 2 pi fct plus kpmt, where fc is equals to 100 kilohertz and kp is given as 20 pi. Then we have to find these parameters, that is maximum instantaneous frequency, minimum instantaneous frequency, total frequency swing, and frequency deviation above fc and frequency deviation below fc. We have to find all these parameters. Now here, first let's find differentiation of mt, because if you see the instantaneous frequency, okay, of PM signal is given by fc plus kp by 2 pi differentiation of mt. So first we have to find out differentiation of mt. So if you see the differentiation of mt, what you will get here is, yes, so I'm going to plot differentiation of mt. Differentiation is nothing but slope. Now what is the slope of this portion? Change in y-axis by change in x-axis. So 4 by 1 millisecond here. Okay, so it is 4 kilohertz. I can say the slope will be. Okay, and what is the slope of this? Change in y-axis is 4 units. Okay, change in x-axis is 2 units. 4 by 2 will be 2. So this is decreasing, means negative slope, minus 2 kilohertz. So if you plot differentiation of mt, okay, so what you can expect is, yes, so it is 4 kilohertz. Okay, and this is minus 2 kilohertz, and this is 4 kilohertz, and this is minus 2 kilohertz, and it's go on like this. So it is the differentiation of mt is what we got now. So we have to find out maximum instantaneous frequency. The first one is, that is Fy max is equals to Fc given how much? 100 kilohertz. Kp is given how much? 20 pi. Let me check once. Kp given 20 pi. Okay, the default units will be radians per volt for Kp. That's okay. Yes, and if you substitute here Kp by 2 pi, 20 pi by 2 pi, okay, that will be 10. Okay, to get Fi max, if the differentiation of mt is maximum positive peak, then Fi becomes Fi max. So what is the maximum positive peak of differentiation of mt? What is the maximum positive peak of differentiation of mt? 4 kilohertz. So this is 4k. So this is 100k plus 4k, 40k. This is 140 kilohertz. This maximum instantaneous frequency. And minimum instantaneous frequency, Fi min. So Fc, yes, it remains same 100 kilohertz, and Kp is 20 pi by 2 pi. This is 10. When Fi becomes Fi min, if differentiation of mt is maximum negative peak, then Fi becomes Fi min. What is the maximum negative peak of differentiation of mt? Minus 2 kilohertz. So this is minus 2 kilohertz. So 100k minus 20k, it will be 80 kilohertz. Okay, now if you see, it is A, B, and finding C. That is the total. C is total frequency swing. So the total frequency swing. Okay, now the resultant PM frequency swings between Fi max and Fi min, and what the total possible frequency swing is Fi max minus Fi min. Okay, will give you the total possible frequency swing of the resultant PM signal, Fi max minus Fi min, and that will be equals to, so what is Fi max minus Fi min here? 140 minus 18, that will be 60 kilohertz. Okay, now D, the frequency deviation above Fc. So frequency deviation above Fc. Okay, so what is the Fc is 100 kilohertz here. This is Fc is 100 kilohertz. Okay, so the resultant PM frequency is deviated from this Fc. So deviated by this much here, deviated by this much. Okay, from Fc. Okay, and above Fc, how much frequency deviation you can see? Above Fc, you can see 40 kilohertz. Okay, above Fc means, if you see Fc, it is it's like this. You can see Fc is 100 kilohertz. Okay, and Fi max is how much? 140 kilohertz. Fi min is what? 80 kilohertz. Okay, now what is the frequency deviation above Fc? That is 40 kilohertz. And frequency deviation below Fc, that is 20 kilohertz. This is what? Okay, now yes, you can say the frequency deviation above Fc, that will be 40 kilohertz. And if you see E, frequency deviation, if the question is frequency deviation below Fc, what is the amount of frequency deviation below Fc? That is 20 kilohertz. And simply, if the question is like this, so the question is like, find maximum frequency deviation? It is the question. Just the question is find maximum frequency deviation. Okay, so that can be above FC, that can be below FC. We don't mind here. Just we have to find what is the maximum frequency deviation from FC. That can be in positive side, that can be in negative side. We don't mind. Just we need what is the maximum frequency deviation from FC. So what is the formula here is, so this is, so what is the frequency deviation from FC? Kp by 2 pi differentiation of mt. It is the amount of frequency deviation from FC, and we need the maximum frequency deviation. So maximum frequency deviation means it is max of, this is Kp by 2 pi differentiation of mt, and it is modulus here. Because here that can be in positive side, that can be in negative side, we don't mind. Just we need maximum frequency deviation from FC. So no importance to sign here. The importance is only to magnitude here. So it will be equals to, yes, Kp is what? 20 pi by 2 pi, that is 10. And what is the maximum peak of differentiation of mt? See here, what is the maximum peak of differentiation of mt? That can be in positive side, negative side, we don't mind. Just we need maximum peak, that's it. So what that maximum peak? Positive side 4k, negative side 2k. No importance to sign, importance is only to magnitude. So positive side 4k, negative side 2k. So what is the maximum peak possible for differentiation of mt is 4k. Okay, so that is 4k here, 4k. So that is 40 kilohertz. Okay, yes, you can see frequency deviation above FC is 40 kilohertz and below FC is 20 kilohertz. Now what is the maximum possible frequency deviation from FC? Maximum possible frequency deviation from FC is 40 kilohertz. This is what is delta F actually, maximum frequency deviation from FC. So in finding maximum frequency deviation, this magnitude will comes into picture. So no importance to sign, importance is only to magnitude. So I hope this question will clarify, okay, is clarify your doubts like how to find Fi max, Fi min, delta F, frequency swing, and frequency deviation above FC, frequency deviation below FC. Okay, so I tried to address these parameters in this question. So take care of this question. I feel it is important for examination. Okay, and if you see the next question. So this next question is MSQ type question, multiple select type question. So here one or more options can be correct. And this question is about receivers. A super heterodyne receiver is tuned to 25 megahertz. Okay, so tuned to 25 megahertz means Fs is given. The intermediate frequency is 10 megahertz. So here intermediate frequency I'm denoting with IF. Now the possible image frequencies we have to find out. And here in this question is FL greater than Fs or FL less than Fs is not given. So I will take both possibilities into consideration here. So for FL greater than Fs, if the local oscillator frequency greater than tuned frequency, then it is also definitely one possibility, FL greater than Fs. Then FSI is equals to Fs plus 2IF. Okay. So Fs plus 2IF means 25 plus 20, this is 45 megahertz. Okay, and another possibility is FL less than Fs. Then image frequency equals to Fs minus 2IF. So Fs minus 2IF will be equals to 25 minus 20. This will be 5 megahertz. Okay, so yes, in this question relation between FL Fs not given, so we have to take both possibilities into consideration. So the possible image frequencies will be 45 megahertz and 5 megahertz, 5 megahertz and 45 megahertz. So here options A and D will be correct here. Yes, it is MSQ type question, one or more options can be correct here. So here A and D will be correct. And if you see the next question here, this next question is about finding bandwidth for the PCM system. Okay, now here if you read the question, a message signal band limited to 20 kilohertz is transmitted by using 10-bit PCM system. Okay, so here FM message signal band limited to 20 kilohertz. FM is equals 20 kilohertz. And 10-bit PCM system, so n value is also given, 10 bits per sample, small n value is given, okay, with uniform quantizer. Find minimum channel bandwidth required. Okay, so for this given PCM system to transmit the resultant PCM sequence, binary sequence, okay, through the baseband channel, a wired channel. So what is the minimum channel bandwidth required? We have to find out if resultant binary sequence represented with represented with here unipolar NRZ rectangular pulse, polar RZ rectangular pulse. Okay, so this question is about if in transmitting a binary sequence, okay, if binary sequence represented by different of electrical pulses, okay, then what will be the channel bandwidth requirement? How the channel bandwidth requirements will be affected? It is a question about. Okay, so here I want to give you some formulas here. What the formulas is? So if you take NRZ pulses, NRZ means non-return to zero. Okay, full width pulses. These are non-return to zero pulses or full width pulses. So in the case of NRZ pulses, okay, even the coding is unipolar. Unipolar is also called as on-off. Okay, or that can be polar, that can be bipolar. Yes, in unipolar, yes, in unipolar or on-off, binary 1 represented by presence of pulse, I'm denoting with PT, and binary 0 represented by 0 volts. And if you take polar, in polar, okay, binary 1 represented by positive pulse, PT, and binary 0 represented by corresponding negative pulse, polar. And bipolar. This bipolar is also called as actually AMI, alternate mark inversion, or this is also called as pseudo ternary coding. In bipolar, 0 represented by 0 volts and binary 1 represented by alternate positive and negative pulses, PT and minus PT. Binary 1 represented by alternate positive and negative pulses and binary 0 represented by 0 volts. Okay, now, yes, so if at all you are using full width pulses in this respective coding mechanisms, okay, then the bandwidth is given by, the bandwidth will be in all these cases, the bandwidth will be equals to RB. Take this as formulas. Binary 1 represented by full width pulse, binary 1 and binary 0 represented by full width pulses, okay, where pulse duration is TB, okay, then the bandwidth is given by RB, bandwidth will be RB. And if you take RZ here, return to 0 or half width pulses. So in this case, the given coding is unipolar or that can be polar, unipolar or polar. The bandwidth will be, okay, 2 RB will be, okay, half width pulses, binary 1 represented by half width pulse where pulse duration is TB by 2 and binary 0 is also represented by half width pulse. Instead of full width pulse, if the binary sequence represented by half width pulses where the pulse duration is TB by 2, then bandwidth will be 2 RB. And whereas if you see, yeah, so if you take bipolar, this is special here, bipolar. So bipolar RZ pulses, in the case of bipolar RZ pulses, bandwidth will be RB only. It is what you have to take care of. Just I want to address this. Okay, so in the case of bipolar, yes, so in the case of bipolar, that can be full width pulses, that can be half width pulses. The bandwidth is given by RB. Bandwidth is given by RB. Okay, and in the case of half width pulses, that is, if at all that is unipolar or polar, the bandwidth is given by 2 RB. Okay, so these formulas you have to take care of. Okay, and these pulses are of course rectangular pulses here. This PT is rectangular pulse and this minus PT also rectangular pulse only. Okay, so here once again I'm saying if the binary sequence represented with full width pulses or NRZ pulses, so irrespective of this coding, any of this coding you use, okay, the bandwidth will be RB, full width pulses. Half width pulses means the bandwidth is 2RB, will be 2RB, but the exception is in the case of bipolar, okay, bipolar RZ pulses, the bandwidth will be RB. Just take care of this. Now come to this. First let's find RB. Okay, RB equals to NFS. N is given how much? 10. Fs. Sampling rate is not given. The default is Nyquist rate. Nyquist rate is 2fm. 2fm means this is 40k. So it is 400 kbps. Okay. Now let's find out the bandwidths here. So unipolar NRZ rectangular pulses. Okay. NRZ means bandwidth is what? Bandwidth is RB. Okay, and one thing, just try to understand this. We have to find the minimum channel bandwidth required. The minimum channel bandwidth required is nothing but signal bandwidth only, because the channel bandwidth what you are maintaining should be greater than or equal signal bandwidth. Then the minimum channel bandwidth required to maintain is equal signal bandwidth only. So indirectly we have to find out the bandwidth, the signal bandwidth of the resultant PCM sequence after representing PCM sequence with electrical pulses. So what is the bandwidth of that binary sequence, PCM sequence, we have to find out. So it is about finding signal bandwidth only, where binary sequence represented by different pulses. So as NRZ means that is RB only. RB is what? 400 kilowatts. Yes, for binary sequence 1 Hz is nothing but 1 bit per second. You can write 400 kilowatts or 400 kbps you can write. And if you see RZ, RZ means bandwidth will be half width pulses. RZ means 2RB, 2RB. So 2RB means what here? RB is 400k. So this is 800 kilowatts. Okay. And for this C here. So NRZ here, full width pulses. Okay. Full width pulses means, okay, the bandwidth is definitely going to be RB only. Okay. So in the case of full width, okay, irrespective of the coding you are using, the bandwidth is given by how much is? The bandwidth is RB only. Okay. So the bandwidth is RB here. Yes. This is RB. And RB is how much? 400. So if the given pulses are full width pulses, NRZ pulses, then irrespective of the coding, the bandwidth is given by RB. And in the case of half width pulses, the bandwidth is 2RB. Okay. But only exception is for bipolar RZ case, the bandwidth is RB only. But this is polar RZ, so bandwidth is 2RB. The next option D is Nyquist pulses. This Nyquist pulses also called as Singh pulses. Nyquist pulses also called as Singh pulses. Okay. So if you represent a binary sequence with Nyquist pulses or Singh pulses, the bandwidth is RB by 2. So RB by 2, it will be 200 kilowatts. Okay. Next, raised cosine pulses with alpha is equals to 0.5. This alpha is actually called as roll-off factor. If binary sequence represented with raised cosine pulses, okay, so with some specific alpha value, then bandwidth is given by RB by 2 into 1 plus alpha. Okay. Now RB by 2 is what? 200k into 1 plus alpha is what here? 0.5. So this will be here 300 kilowatts. Okay. So this is how you can find out the PCM bandwidth, where binary sequence is represented by different pulses. Okay, it is important model of question. If you see the next question here, this next question is about FSK. Here, the FSK waveforms given here. Okay, AC cos 20 pi into 10 power 3t and S2t. Okay, this is AC cos 16 pi into 10 power 3t plus pi. Okay. So here binary one represented by high frequency sinusoidal pulse here, and binary 0 represented by low frequency sinusoidal pulse. So what is the frequency here? High frequency is how much? FH is 10 kilohertz. FL is equals to, this is 8 kilohertz. And here, what is the question about here is, between FSK waveforms you can see some phase shift, and phi not equal 0 here means some finite phase shift exists between FSK waveforms. If some finite phase shift exists between FSK waveforms, this FSK, what you say, is called as a non-coherent FSK. So this FSK is non-coherent FSK. Now we have to find maximum value of bit rate to meet orthogonality between FSK waveforms will be, okay, how many kbps we have to find out. So for this FSK waveforms to be orthogonal to each other, this orthogonality is also called as uncorrelation. You have to understand this. In communication terminology, orthogonality is nothing but uncorrelation only. So for FSK waveforms to be orthogonal to each other, what is the maximum bitrate allowed? We have to find out. Okay. So for non-coherent FSK, what is the condition to maintain orthogonality between FSK waveforms? FH minus FL is N by TB. So that is NRB. Okay. Yes, we have to find out RB here. RB is equals to FH minus FL by N. So FH minus FL. FH minus FL is 10K minus 8K. This will be 2K by N, where N is an integer. So this N can be 1, 2, 3, 4. Can be any of these integers. N can be any of these integers. Now to get RB max, the maximum bitrate allowed, we have to find out. To get RB max, N should be minimum. What is the minimum N we can go for? Is 1. So this is 2 kbps. Okay. So what is the maximum bitrate allowed is 2 here. We have to find in kbps. So the answer will be 2 here. Okay. And here another possibility here is, if the question is like this, what is the question is, if phi is 0, same question, but if phi is 0, phi 0 means here what? There is no phase shift between FSK waveforms. If there is no phase shift between FSK waveforms, this FSK is called as coherent FSK. Okay. And for coherent FSK, what is the condition to be maintained to maintain orthogonality between FSK waveforms is FH minus FL is N by 2 TB. This is okay. Now this FH minus FL equals to NRB by 2. Then RB is equals to, this is 2 into FH minus FL by N. Then what is RB max? I'm doing the same question, but with phi is equal 0 here. So 2 into FH minus FL is 2K. To get RB max, N should be minimum. What is minimum N we can go for is 1. So this is 4 kbps. The answer will become 4 kbps provided phi is equal 0. So it is important here, okay, for FSK. So it is the condition for orthogonality in the case of non-coherent FSK, and this is condition for orthogonality in the case of coherent FSK. Okay. Now if you see the next question here. So this question is about finding entropy at the quantizer output. Okay. Here the sample of stationary random process having the PDF. Here sample of random process means that is random variable only. If you sample random process, that will give you a random variable. Here the density function of random variable is given. Fx of x is k delta x by 2. So if you plot it, so it will be fx of x with respect to x. So delta x by 2. So what you see in the denominator 2 here. So it is a rectangular pulse. Delta function means here the denominator is 2 now. So this is from -2 to 2. And what is the height here is k. So it is the density function of x given. And this random variable x given to 4-level quantizer, okay, described as below. 4-level quantizer. So 4 quantization levels available with the quantizer. Okay, so here the output of quantizer is given. Qx means you can understand as the output of quantizer. Yes, at the output of quantizer you will get quantization levels. So these 4 possible quantization levels given here. Okay, so here this x is given to quantizer. Okay, 4-level quantizer. So what are the quantization levels available here? The quantization levels available minus 1.5. This is minus 0.5 and 0.5 and 1.5. Okay, so I'm denoting with here Q1, Q2, Q3 and Q4. So these 4 quantization voltages available with the quantizer. So the output of quantizer can be any of this provided x value. Okay, if x value in between 1 and 2, the quantizer output is 1.5. If x value in between 0 and 1, that x will be quantized to 0.5, like that. So here, so if you see the dynamic range of this random variable here, what are the range of values possible for x? That is minus 2 to 2. Minus 2 to 2. Okay, now if you see, if x is in between minus 2 and minus 1, minus 2 and minus 1, and that is quantized to, I'm denoting with q, minus 1.5, that is rounded off to minus 1.5. And if x is in between minus 1 and 0, minus 1 and 0, then that is quantized to minus 0.5. Okay, now if x is in between 0 and 1, then that will be quantized to 0.5. And finally, if x is in between 1 and 2, that will be quantized to 1.5. So depending upon this x value, the quantizer output can be any of this. Now we have to find entropy at quantizer output. So to find the entropy, we need probabilities. So what is the probability for Q1 at the output of quantizer? What is the probability of Q2 at the output of quantizer? We have to find out. So here let's find out PQ1. So what is the probability of Q1 at the output of quantizer? When you expect Q1 at the output of the quantizer, Q1 is what here? Minus 1.5, minus 1.5. Provided x is in between minus 2 and minus 1. So it is nothing but minus 2 less than or equals to x less than or equals minus 1. If x is in between minus 2 and minus 1, then you expect Q1 at the output of quantizer. How to get probability? Okay, from the density function. Density function of x is given, then we have to find the probability. The area under density function will give you corresponding probability. So this is minus 2 to minus 1 fx of x dx. Okay, now if you see, if you try to find out k value here, the total area under density function should be equals to 1. So in that way you can find k value, that is 1 by 2. Okay, so if you try to get this line equation from this line equation, if you try to get this line equation, so what is fx of x where x is in between minus 2 and 0? This is the line joining 2 points. So this is, so this point is minus 2 comma 0 and this point is 0 comma 1 by 2. The line joining 2 points, if you see, you will get minus x plus 2 by 4 is what you will get. Okay, and if you see, and the line, this line equation, if you see, this is x plus, yes, this is you will get x plus 2 by 4 and this is minus x plus 2 by 4, the line equation you will get. Okay, this line joining these 2 points. Okay, this line equation like y minus y1 equals to y2 minus y1 by x2 minus x1 into x minus x1, then you will get this line equation is what you're going to get. Okay, now so fx of x is x plus 2 by 4 where x is in between minus 2 and 0, and fx of x is minus x plus 2 by 4 where x is in between 0 and 2. Now it will be equals to now, yes, so when x is from minus 2 to minus 1, what is fx of x is x plus 2 by 4, and if you substitute and if you do it, then you come to know this is 1 by 8 is what you're going to get. Okay, so one thing, the probability of x is in between minus 2 and minus 1, the probability of x is in between 1 and 2 is going to be same only. How to get probability from density function? Area. So this area of course will be same as this area. So the probability of x is in between -2 and -1. The probability of x is in between, okay, 1 and 2 is going to be same only. Okay, so in this way I can say PQ1 will be equals to, okay, the probability of x is in between 1 and 2 and x is in between -2 and -1 is same. So I can say the probability of this Q1 and Q4 will be same. The chances of this Q1 and Q4 will be same. So PQ1 equals to PQ4 equals to 1 by 8. Okay. Now if you see, similarly PQ2 is same as PQ3. So the chances of Q2 and Q3 will be same. Okay. So what is the probability of is going to be same, of course. Yeah. If you try to find out, yeah, PQ3 for example, what is the chance for Q3 at the output of quantizer? Q3 means what? 0.5. So to get 0.5 at the output of quantizer, x should be in between what? 0 and 1. If x is in between 0 and 1, then the output of quantizer is 0.5. So the chances of 0.5 Q2 at the output of quantizer is nothing but the chances of x is in between 0 and 1. So this is probability of x is in between 0 and 1. So this is integration 0 to 1 fx of x dx. Okay. So when x is in between 0 and 1, what is fx of x? Minus x plus 2 by 4. Just substitute here, and if you try to find out, you will get 3 by 8 is what you're going to get. Now we got the probabilities here. PQI is equals to, what the probabilities? PQ1 is 1 by 8, PQ2 is 3 by 8, PQ3 also 3 by 8, PQ4 is equals to 1 by 8. So we got the probabilities. So once we got the probabilities, yes, we can find out the entropy. H will be equals to, what is the entropy at the output of quantizer? That is summation I PQI. This is log, okay, PQI base 2. So it is of course minus. So this is how you can find entropy. Okay, summation PQI log PQI, and this will be minus. And if you substitute, this is 1 by 8, 1 by log 1 by 8 base 2. And if you see this term, it is also 1 by 8 log 1 by 8 base 2. So into 2 I can write plus. And this is 3 by 8 log 3 by 8 base 2 of course. And it is also 3 by 8 log 3 by 8. So it is into 2. So if you find this, so it comes to be, what is the answer you're going to get here is 1.8113. This is, it is bits per sample. Okay, so here we are finding entropy for the quantized samples. Okay, so the units of entropy will be bits per sample, and if you are dealing with symbols, then the units of entropy will be bits per symbol. But here we are dealing with samples here, quantized samples. The units of entropy will be bits per sample. Okay, so here this is about finding the entropy at the output of quantizer, and this is the procedure. Okay, so what will be the probabilities for this quantizer levels we have to find out. Okay, so once we got those probabilities, yes, we can proceed to find out the entropy like this. So it is also important model of question. Okay, now if you see this question here, the channel diagram is given for a system here. Okay, the transmitted symbols will be here M0, M1. The possible received symbols will be R0 and R1. Okay, and the corresponding conditional probability is also given. The probability of M0 received as R0, that is 1 minus P, M0 received as R1, P, like that. The conditional probability is given, and the source probability is also given. P M0 and P M1 is given. Okay, a decision device is connected at the receiving end of this channel, which makes a decision in favor of M0. Okay, when the received symbol is R0. Okay, so if the received symbol is R0, then decision is taken in favor of M0. If R0 is received at the receiver side, the decision device which is used at the receiver side will make the decision in favor of M0, provided R0 is received. And in favor of M1, when the received symbol is R1. So if R1 is received by the receiver, then the decision will be taken in favor of M1. Okay. And if the decision device set to be optimized according to map criteria. Okay. So here this decision, what you see, R0 in favor of M0, R1 in favor of M1. Okay. So this decision will be taken here by using map algorithm here, map decision algorithm. Okay. Then the sufficient condition to be satisfied will be, we have to find out. Okay. So here, yes, of course, here PM0, the source probabilities are different here. Okay. If source probabilities are different, then the decision decoding of the received symbols, okay, means making the decisions in favor of source symbols, means if R0 is received, the decision should be taken in favor of M0 or M1, and if R1 is received, the decision should be taken in favor of M0 or M1. So this is what you see is also called as decoding of received symbols. Okay. Yes, we have to decode the received symbols at the receiver side. This R0 and R1 should be decoded in favor of M0 or in favor of M1. Okay. Such that the probability of error should be as minimum as possible. So for this we take the help of decoding algorithms. Okay. So one is map decoding, another one is ML decoding. If source probabilities are different here, okay, the algorithm what we use is map decoding, and if source probabilities are equal, then the decoding algorithm what we use is ML decoding. Okay. And here source probabilities are different, so which decoding technique is used here is map decoding technique is used. And so if map decoding technique is used, okay, and to make, okay, decisions like this, to get the decisions like this, R0 should be decoded as M0 and R1 should be decoded as M1 by using map decoding algorithm. So to get this results, okay, which of these conditions should be satisfied, we have to find out. Okay. Now if you see here, yes, so let M0, yeah, let R0 is received. Let's proceed like this. Let R0 is received. To receive as R0 two possibilities, that is M0 emitted and M0 received as R0. It is one possibility. Another possibility is M1 emitted and M1 received as R0. Here two possibilities for R0. And here the requirement is R0 should be decoded as M0. Okay. So for R0 to be decoded as M0, so it should be greater than. Okay. So if it is greater than here, I can say to receive R0 at the receiver side, M0 is having more chances compared to M1. Then R1 will be decoded as M0. So for R0 to be decoded as M0, so this condition to be satisfied. Okay. So now PM0, if you substitute, this is 0.7. R0 by M0. R0 by M0 is 1 minus P. Okay. It is 1 minus P. Okay. Greater than PM1. PM1 is what? 0.3. And PR0 by M1. What is PR0 by M1? This is Q. Okay. And if you simplify this, you come to know this will be 7P plus 3Q less than 7. Okay. So this is the condition to be satisfied. Okay. For R0 to be decoded as M0. Okay. This is the condition to be satisfied for R0 to be decoded as M0. Okay. Next, let's take the second case, that is let R1 received. Okay. And for R1 to be received at the receiver side, what are the conditions to be satisfied? What are the possibilities? What the possibilities is? One possibility is M0 emitted, M0 received as R1. This is one possibility. Another possibility is M1 emitted and M1 received as R1. And here the requirement is R1 should be decoded as M1. For R1 to be decoded as M1, what is the condition to be satisfied is it should be less than like this. Okay. Then you can see to receive as R1, M1 having more chances here. So R1 will be decoded as M1. So this is the condition to be satisfied. And if you substitute the respective values here, P M0 is 0.7 and P, yes, R1 by M0. What is P? Yes. What is P R1 by M0? This is P less than P M1. P M1 is 0.3. P R1 by M1. R1 by M1 is 1 minus Q. Then you come to know this is 7P plus 3Q less than 3. So this is the condition to be satisfied for R1 to be decoded as M1. This is for R1 to be decoded as M1. This is for R1 to be, yes, to be decoded as M1. This is the condition to be satisfied. Okay. Now, to make both the decisions here, the requirement is to make both of these decisions, what the condition to be satisfied? Means this condition to be satisfied and this condition also should be satisfied. So 7P plus 3Q should be less than 7 here if you take 7 here and if you take 3. So this, so for both conditions to be satisfied, 7P plus 3Q, what you say, should be less than, it is 3 here. Yeah, this is 3 and this is 7, you can say. Yeah. So it should be less than 7, at the same time less than 3 also. Less than 7, less than 3. So less than 7, less than 3 means what is common here? Less than 3 will be the common here. So which satisfies both here is 7P plus 3Q less than 3. Okay. So which is common to both here is should be less than 7, should be less than 3. Which is common to both here is less than 3 will be common here, I can say. So for this decoding to be done like this. Okay. So what is the condition to be satisfied here is to satisfy both results here. What the condition to be satisfied is 7P plus 3Q should be less than 3 here. So less than 3. So here which option will be correct here is option B will be correct here. Okay. And if you see the next question here. So here in a binary communication system, okay, equal probable bits are transmitted through an IC channel. Okay, equiprobable bits. The variable at the input of the decision device in the receiver is given by R is equals to X plus N. Okay, the input of the receiver. Okay, yes. So at the receiver side, the threshold device will be there, threshold comparator will be there, and the input is given by R, that is X plus N. The transmitted symbol X takes the values plus alpha minus alpha for logic 1 and logic 0. Okay, so it is V threshold, you can say. If R greater than V threshold, the decision will be taken in favor of 1, and R less than V threshold, the decision will be taken in favor of binary 0 here. So it is a binary system, means transmitting binary 1 and transmitting binary 0 here. Yes, if you see in transmitting binary 1, I'm denoting with H1, hypothesis 1. The transmitted symbol X is plus alpha, and in transmitting binary 0, so X is equals to minus alpha. The transmitted symbol is minus alpha. And here the noise variable is uniformly distributed in the range -3 to 2. Okay, so if you see the density function of noise, this is -3 to 2. Uniformly distributed, density function is constant like this. Then what is the height will be, of course, 1 by 5 will be. Okay. Now if the value of alpha is selected such that probability of error can be made 0 by choosing proper threshold value, then minimum value of alpha should be, we have to find out. Okay, so here if probability of error Okay, if you find probability of error with optimum threshold, and you have to get probability of error 0, you have to get. And to get probability of error 0 here, that is a requirement. Okay, so what is the minimum value of alpha should be, we have to find out what minimum value of alpha should be, so the probability of error will become 0. Okay, is what we have to find out. So here pH1 is equals pH0 is given in the question. The symbols are transmitted with equal probability. Here you can see in the first line it is given equal probable bits are transmitted through a noisy channel. Okay, so the symbols are transmitted with equal probability. Okay, now first we have to get the density function of R here. So the decision will be taken in favor of 1, in favor of 0 based on R value here. So first we have to get the density function of R here. Okay, so here in transmission of 1, R is equals to x plus n, of course. But in transmission of 1, x is what here? Alpha plus n. Okay, and in transmission of 0, so what is the received value? R is equals to x plus n, where x is minus alpha. Okay, alpha is some constant, of course. Now if you see the density function of R when 0 transmitted here, so fr by 0, density function of R when 0 transmitted. Okay, so here, so I need the density function of R when 0 transmitted. So if you add some constant to your random variable, density function is just shifted. Okay, so here what are the values possible for n here? N can be any value between -3 and 2. And if you add minus alpha to this n, what the resultant value will be? The resultant value will be -3 minus alpha, 2 minus alpha will be. The values possible for n will be can be any value from -3 to 2, and I'm adding some minus alpha to this n. If you add minus alpha, the resultant R can be any value between -3 minus alpha to 2 minus alpha. So this is -3, I can say minus alpha and 2 minus alpha. Okay, the height of course will be how much here is 1 by 5, of course. Just density function is shifted, that's it. Okay, now what is the density function of R when 1 transmitted? If you see fr by 1. Okay, so when binary 1 transmitted, R is equals to alpha plus n. Okay, and if you add some alpha volts to n, what the resultant will be? So if you add some, the values possible for n will be in between -3 and 2. And if you add alpha volts to this, so -3 plus alpha and 2 plus alpha, this is. So it can be any value between -3 plus alpha and 2 plus alpha. The height is of course 1 by 5. Okay, this is. Yes, generally what you expect is when binary 0 transmitted, R will take low values comparatively, and when binary 1 transmitted, R will take high values. Okay, and to get probability error 0, to get P0, okay, there should not be any overlapping between these two density functions. There should not be any overlapping. Okay, so there should not, there shouldn't exist, should not exist any overlapping between these conditional density functions, between fr by 0 and fr by 1. Okay, so what is the input of the threshold comparator here? R. You have to understand this. Okay, based on the R value only, the decision will be taken in favor of 1 and in favor of 0. And in the process of making decisions in favor of 1 and 0, to get the 0 probability of error, no probability of error. Okay, so what the condition to be satisfied is there should not be any overlapping between these two conditional density functions. That is a requirement. So for this I can say this 2 minus alpha, okay, should be less than or equals to -3 plus alpha. This is. So this, yes, when binary 0 transmitted, Okay, R takes low values here. Okay, and when binary 1 transmitted, R takes high values. So if you plot both density functions in a single plot, so it should be like this. Both density functions in a single plot. This is 2 minus alpha and this is minus 3 plus alpha. So this is FR by 0 and this is FR by 1. This is okay. Yes, when binary 1 transmitted, R takes high values comparatively. When 0 transmitted, R takes low values comparatively. And what is the requirement is there should not be any overlapping between these two density functions. This is the requirement. And to satisfy this, I can say 2 minus alpha, okay, should be less than or equals to minus 3 plus alpha. If 2 minus alpha greater than minus 3 plus alpha, then some overlapping will exist between these two density functions, and you can expect some finite amount of probability of error. And to get zero probability of error, there should not be any overlapping. So 2 minus alpha should be less than or equals to minus 3 plus alpha. So from this, you will come to know. So this is 2 alpha, okay. So less than or equals to 5. So alpha less than or equals to 2.5. This is alpha should be less than or equals to 2.5. Okay. Now what we have to find out here, the minimum value of alpha should be, yes, if you see this is, yes, 2 minus alpha should be less than or equals to minus 3 plus alpha. Okay. So this is here. Yeah. So alpha goes this side. 2 alpha should be greater than or equal to this is. Yes, no? Yes. Should be greater than or equals to. So alpha should be greater than or equals to 2.5. So alpha minimum is 2.5. So 2.5 will be the answer here. Okay. So take care of this model of question. So I feel this is important. So just the thing I want to convey for you here from this question is to get zero probability of error, there should not be any overlapping between conditional density functions. Conditional means FR by 1, FR by 0. Between those two density functions, there should not be any overlapping. Then probability of error will become 0. Okay. So you have to take care of this. Okay. So yes, these are some important questions here from communication systems. Okay. I try to give some important model of questions within this short span of time. So I hope these questions definitely will helpful to you in the coming GATE examination. So all the best students, and best of luck.